So my talk today is all about building consensus, really focused on ASTM consensus, the road to an ASTM biochar standard for concrete. Let's start with the big picture. Why are we even considering putting biochar in concrete? I know John touched on this a little bit. I'll go into it in a little bit of a different way. Concrete is the most widely used construction material on the planet. As such, it's responsible for 8% of global CO2 emissions. That means it's the third largest single source emitter of CO2 for any individual industrial activity. The concrete industry has really been trying to decrease its carbon footprint for many years now, but this has been a real challenge for the industry because of its reliance on cement. That's one of the key ingredients in concrete, and it's the material that binds all of the other ingredients together. It's hard to decarbonize the cement industry because the carbon footprint is tied to the material itself. The CO2 is released during the process of converting limestone, calcium carbonate, to free lime, calcium oxide, which releases CO2 in the process. So unless the concrete industry stops using cement, the basic building block of concrete, we're really stuck with these emissions. And I wanted to find a way to change the narrative about concrete in this way. So getting back to the question, why biochar in concrete? By replacing a portion of the cement in concrete with biochar, we reduce the demand for the most carbon-intensive component of concrete, and we store carbon that would be otherwise released into the atmosphere. So if we can put enough biochar in concrete, we can completely eliminate 8% of global CO2 emissions. That's equivalent to parking every passenger vehicle on the planet permanently. But to do this, we have to have buy-in from the concrete industry. And that requires proof, trust, and consistency. In practice, every major project that uses concrete requires the materials used in the concrete to meet ASTM standards. Without them, every project has to have their own suite of testing for the materials, and the engineers face risk and uncertainty. Standards reduce this risk, build trust, and create pathways for broader use. In the case of biochar, a standard will tell producers how to qualify their material. It'll guide engineers how to specify it, and it'll give contractors confidence that performance requirements are met. It's the seal that people trust to say this material does no harm to my concrete. But with a material so versatile and so different than conventional concrete materials, what testing should be required for biochar? Across academia and industry, research on biochar in concrete has exploded in recent years. When I first started in 2019, there was only a handful of papers. That has grown exponentially. I can no longer keep up with the amount of things that are being published on this. We've seen some evidence of strength improvements in some cases, durability gains in others, and of course, carbon footprint reductions almost across the board. But results are highly variable. I can name countless examples of the opposites of all of what I just listed. Feedstock differences, pyrolysis conditions, and particle properties all affect performance. For example, one of the durability tests that's often required for concrete materials is alkali-silica reactivity. Without boring you with all the details of what this reaction is, this is one of our biochar mortar samples that we put through alkali-silica reactivity testing. If you're saying, yuck, that's right? This does not look very good. This would not pass this test. Whoop. This would not pass the alkali-silica reactivity test. Without again, going into all of the details for this, what I would say is that we've shown both good and bad results for alkali-silica reactivity testing. And the interesting thing is that what we're observing here, we don't actually even think is alkali-silica reactivity. So the test we're doing is designed to measure that property. We're getting bad results according to the test, but we don't actually think what we're seeing is alkali-silica reactivity. Some of these tests that are required for certification of concrete materials might not apply for biochar-based materials. But these tests will still be required to prove to the industry that the material does no harm. Keep in mind that standards aren't neutral. They're built on assumptions by people, and when we introduce new materials, we have to ask ourselves whether those assumptions still apply. So I'm going to give you an example that's unfortunately a little close to home, my driveway to be exact. A couple of years ago, in a massive coordinated effort by the cement industry, the industry switched from a Type 1-2 cement to a Type 1L cement. Type 1L cement is really only different that in a portion of it is now a ground limestone instead of all kind of a Portland cement-based cement. They are great under certain applications. They perform just as well as Type 1-2 cements, and they have a lower carbon footprint, so it seems like a win-win. And for the most part, it was really touted as a one-to-one replacement. So exactly the same, just replace this Type 1-2 cement with a Type 1L cement and you're good to go. But in practice, many concrete finishers noticed a higher water demand for the product. It turns out that Type 1L cements release their bleed water a little later than Type 1-2 cements. And that bleed water is the water that rises to the top after the particles settle. So it's what finishers call the cream that allows you to kind of finish off a nice smooth surface on the concrete. However, if you finish the concrete too soon before that bleed water rises, then all you do is trap the water underneath. And so you're left with a really porous surface layer that flakes off afterwards and leads you to something that looks like my driveway. It's very embarrassing to be a concrete material scientist and have a driveway that looks like that, by the way. So don't hear me bashing Type 1L cements. I think it's been good for the industry. It has legitimately lowered the carbon footprint of concrete. But I think we've made a mistake in not engaging properly with the stakeholders across the industry and assuming too much about how similar the materials would behave. Surface scaling is one thing. It's unsightly, but structurally it's fine. But structural integrity is another. So as we start considering incorporating these new materials into our concrete, we really have to be careful about how we evaluate the assumptions that go into our testing and our interpretation of data. We have to ensure we handle new technology carefully and responsibly. So let me give you another example of where one of our assumptions didn't hold about biochar, because we've seen lots and lots of these in our testing. And again, we've seen contradictions to it as well. It's a really variable material. In our work with biochar cementitious composites, we've found that electrical resistivity and permeability don't always correlate in the way that you would expect in conventional systems. And in case you're not familiar with this relationship, allow me to just explain briefly. Professors like to profess. In conventional concrete, electrical charge travels through the cement pore solution, so it's really closely tied to its permeability. That means the same pore network that facilitates electrical charge through the concrete also facilitates water travel through the concrete. So when you have a high resistivity material, the assumption is that you have a low permeability material. However, in the case of biochar, we do not always see that this assumption holds. So let's consider this data for a moment. This is a plot of water penetration depth versus bulk electrical resistivity. So on the y-axis, it's basically an unambiguous measurement of permeability, and then we have this bulk electrical resistivity measurement that's a quick test that's used as a proxy for permeability. The way that we conduct this test is we take a cylinder, we subject it to pressurized water flow for 3 days, split it open, and measure how far the water has penetrated. So a really simple test. At the intersection of these two lines is our control mortar with no biochar. So according to conventional wisdom, an increase in bulk electrical resistivity should correlate with a decrease in permeability, while a decrease in electrical resistivity should correlate with increased permeability. But instead, we show that in some cases, the biochar can both reduce permeability and reduce electrical resistivity. In this case, the decreased electrical resistivity is attributed to an increase in pore solution conductivity, as ions from the biochar make their way into the pore solution. And so in literature, we can see claims that biochar can make concrete conductive. This may be true. We have not seen it. without verifying that the electrical resistivity decrease is caused by a percolating solid network of that conductive filler throughout the concrete, it's equally likely that the biochar is simply increasing the ionic strength of the concrete, or worse, increasing the permeability. The reason why I say worse is because that would have implications for long-term durability. As we introduce new materials, we need to be incredibly thoughtful about the way that we apply what we know about conventional systems. We need to understand the assumptions of the models or standards from conventional systems, and we need to ask how the new materials might violate those assumptions. Another example where our assumptions were not met by biochar is from freeze-thaw testing, so I'm glad that came up. Here again, we assumed the rules would hold, and they didn't. Again, conventional wisdom tells us that if concrete is sufficiently air-entrained, it should be protected against freeze-thaw damage. The air voids help reduce the tensile stress experienced by concrete as water in the pores freezes. So as ice crystallizes, the water is displaced into a nearby air void, and it can grow without causing expansive pressures that damage the concrete. Typically, if we have 6 volume% air and a spacing factor of 200 microns, spacing factor is basically the average distance the water has to flow into a void. So 6 volume%, 200 micron spacing factor, that typically means that the concrete is protected against freeze-thaw damage. However, when biochar is added to the concrete, the rule doesn't seem to hold. So in this plot, we've got freeze-thaw results from 300 cycles for the sample who made it to 300 cycles. So on the y-axis, we have relative dynamic modulus of elasticity versus the number of freeze-thaw cycles. That relative dynamic elastic modulus, just think of that as a comparison to the original. So if it's at 100%, that means the sample hasn't cracked at all during the freeze-thaw cycles. Anything lower than that means that there's been some damage through the successive freeze-thaw cycles. So we can see, if we look at the blue data here, that's our control, so no biochar. If we look at that, we can see that it performs really well. At the end of 300 cycles, it's still a 90% relative dynamic modulus of elasticity. For the orange and red, we see something different. They did not perform so well. Around 150 cycles or so, we've actually failed the test. So that red line here indicates the point of failure. Now, when we cross-sectioned these samples, we found that it had the requisite air void system. So what happened? Honestly, we're still trying to understand why. This is violating our assumptions. We haven't seen this before. We're trying to understand it. And this has been a material that's really challenged our assumptions from the very beginning and consistently continues to do so. Now that we know this is a potential issue, we can protect the concrete industry against it by standardizing it, by requiring this testing specifically for our ASTM standard. But had we not tested it, would we have anticipated adding this to the specification? Almost certainly no. This is not a common requirement for material specifications. But as innovation accelerates in the rush to decarbonize the concrete industry, we really need to be thoughtful and evaluate what assumptions we might be making that might not hold anymore. Innovation is never without risk, and I would say the risk in this case is absolutely worth it, because what we're trying to do is something of massive impact, but we need to be thoughtful about it. Now, you might be all thinking, like, why are we even here? It sounds like biochar is terrible for concrete. You know, this is a biochar conference. It's not all doom and gloom. Rest assured, there are ways to make biochar work without sacrificing any concrete performance. I'm highlighting some bad actors here as a cautionary tale. If this weren't true, I wouldn't be wasting my time starting a company, right? We've figured out ways to make this work. But there are also lots of ways for biochar not to work. And a standard must prevent any bad actors from penetrating the concrete market. So please hear me, not all biochars do no harm, or to put it another way, some biochars do harm concrete. And we have to have every precaution not to have those in the concrete industry. The concrete industry right now is receptive to biochar. That's great news for the biochar industry. But to maintain that openness, we can't have any bad actors enter into the market and give biochar a bad name. So please don't assume your biochar will work. Get it tested. The ASTM standard for biochar use in concrete will certainly help give you guidelines on what to test. So keep your eyes out for that, and I'll be sure to communicate that to the biochar community when that's available. So what are some other challenges for standardization? So first, there's the feedstock variability. Biochar made from wood is different than biochar made from agricultural residues. You all know this very, very well. And then second, as you've seen, we've observed lots of situations where biochar violates standard assumptions. So we need to be careful applying old assumptions to these new materials. I know I sound like a broken record, but I really want to just drive that home. Third, we really do need reliable test methods for materials and performance characterization. The alkali silica reactivity test was a great example. It's measuring something, but it's not alkali silica reactivity. So if we want to measure alkali silica reactivity, we need adapted tests. That's just one example, but there are many others like it. And ultimately, we do need to ensure that we do no harm to the concrete. But there's endless testing that could be specified, right? Do we need to do them all for biochars? That would be very costly for the biochar producers and would probably be a great hindrance to widespread adoption. So we need to be sensitive to striking the balance between having our concrete protected, making sure the biochar does no harm, and not being overly burdensome on the testing requirements. The good news is that ASTM provides a proven framework for tackling these issues. I won't go into all of what I wanted to say on this. I'm getting short on time. But what I really do want to highlight here is please get involved with ASTM. ASTM works best when there's a community of people from all different parts of the industry that are working together to make sure that we're making a standard that meets everyone's needs. You know, if no biochar producers are involved in it, then all the concrete industry is going to do is tell you to test everything, right? That's not going to be to your benefit. We need everyone involved to get that input and make sure that it's a good standard that people can actually use to protect concrete, but also that's practical. Its standard is C928, so please look that up. Everyone's free to join. You don't need permission, and I would love to have your input. Quickly, what do we know the biochar standard will include, and what do we think it will include? What we know it will include from our first meeting is that there's going to be types of biochar. There are types of biochar for use in concrete, sorry. That's primarily going to be based on a particle size and carbon content. There's also going to be labeling requirements, indicating whether the carbon attribute is attached or if it's already been sold. Please know carbon credits are pretty unfamiliar to the concrete industry. And so you need to be like really explicit about that if you've sold your carbon credits. They are not going to know that. So we're going to have some language there. There's also going to be some report-only requirements for biochar composition. And there's certainly going to be performance test requirements. You can bet on that. What those look like, we're not sure yet. Something like a strength activity index, something like a reactivity test, those are going to be in the standard as well. From our last meeting, it's also likely there's going to be some additional requirements. Some of them will be report only, just different compositional things like ash content, alkali content, chlorides, things that we know historically have impacted the quality of concrete. There's also going to be some uniformity requirements. So is your batch to batch variation within some tolerance? So you can expect that as well. There's certainly going to be some durability testing requirements. The durability tests specifically are kind of cumbersome. You can imagine those are the ones that take the longest. You've got to collect some data over time. And so we have to be careful not to over-specify things that don't need to be specified, but do specify the things that do need to be specified. So that's going to take some additional testing, but you can expect there's going to be something there. To close, the journey to an ASTM biochar standard for concrete is both a challenge and an opportunity. It's about more than just testing protocols. It's about creating the foundation for carbon negative concrete to scale. By building consensus across research, industry, and end users, we can make biochar not just a promising idea, but a trusted material in concrete worldwide. We can create a massive, unprecedented demand for biochar. Thank you, and I look forward to your questions and discussion. I also wanted to thank my students who have contributed all this work. I've only included the student pictures who got particularly dirty doing biochar, because I feel like they should be recognized for their hard, dirty work.